Launching a body into the air requires overcoming massive downward forces. To survive the sheer physical strain of takeoff and sustained flight, an animal needs high structural strength. But to actually generate lift, it requires the minimum possible physical mass. The avian skeleton evolved to solve this specific bioengineering paradox. It is a specialized, derived system that balances these two opposing mechanical demands. You can observe the results of this specialization at a glance. We find unique landmarks like the fused skull, the furcula, a massive keeled sternum, the fused sensacrum and pygostyle, and highly condensed limb bones like the carpometacarpus and tibiotarsus. These visible landmarks are driven by specific physiological changes occurring at the microscopic level. Every feature of the bird's framework is a calculated evolutionary trade-off, replacing generalized mammalian flexibility with the physical rigidity required for aerial survival. To understand how this works, we have to look past the top-line anatomy and examine the internal architecture of the avian wingbone, specifically the humerus. This split screen compares a dense mammalian bone against a hollow avian humerus. Inside the avian bone's thin cortical shell, a fine network of trabecular struts bridges the empty space. This truss system maximizes rigidity by distributing torsional and compressive forces, adding strength without mass. We can verify the specific aerodynamic purpose of this adaptation by looking at flightless diving species like penguins. They retain dense marrow-filled bones to increase weight and stay underwater. But in flying birds, the hollow voids created by this truss architecture are physiologically active zones. Weight is reduced by engineering the remaining bone mass to sit exactly where aerodynamic stress demands it, repurposing the internal space for metabolic function. The hollow cavities of the avian skeleton are inarticulately integrated with the bird's respiratory tract. Air sacs branch from the lungs, sending specialized extensions called diverticula into the core cavities of the humerus, sternum, and vertebrae. These pneumatic bones are actively ventilated, receiving continuous airflow through their hollow interiors during both inhalation and exhalation phases. This internal ventilation supports the rapid oxygenation of the blood, generating the metabolic energy required to sustain flight. The resulting weight savings are significant. In many flying species, the total mass of the external feathers exceeds that of the entire skeleton. However, this interconnected system introduces a clinical vulnerability. Pneumatization creates a direct highway for opportunistic bacteria in the respiratory tract to migrate deep into the skeletal core. This displays the effects of bacterial chondronecrosis with osteomyelitis, or BCO. Panels A and C show the smooth articular cartilage of a healthy joint. Panel D reveals what happens when pathogens travel through respiratory pathways and colonize the bone, destroying tissue from the inside out. The pneumatic skeleton provides an aerodynamic advantage while simultaneously creating a pathway for systemic infection. Taking that lightweight frame into the air relies on the mechanical engine located at the avian shoulder joint. Any flying object must keep its center of gravity low to maintain stability in turbulent air. This stability problem is solved by the triosseal canal. Here, the coracoid, the scapula, and the furcula converge to form a specific bony opening in the shoulder. Below this opening, anchored to the keeled sternum, sits the supracoracoideus muscle. This creates a mechanical challenge. The muscle needed to pull the wing up is positioned below it. The supracoracoideus solves this by sending its tendon through the triosseal canal. The bone acts as a biological pulley, redirecting downward contraction into upward lift. During these strokes, the paired furcula flexes outward and snaps back inward, acting as a mechanical leaf spring to conserve kinetic energy. By utilizing these bony pulleys, the avian skeleton centralizes massive muscular weight for stability without compromising the force needed for flight. Mammals rely on segmented joints for articulation. Birds deploy a strategy of fusion to survive airborne shear forces. This compares the bending sections of a mammalian spine with the rigid avian skeleton. The avian spine undergoes significant fusion. Vertebrae merge directly with the pelvis into a solid block known as the sensacrum, while tail segments compress into a single pygostyle. This fusion strategy repeats in the distal limbs. The complex bones of a typical vertebrate wrist condense into a single carpometacarpus, and the ankle bones fuse into the tarsometatarsus. This skeletal rigidity soars on vital mechanical function. Locking the joints eliminates the need for the heavy musculature normally required to stabilize flexible segments under stress. skeletal fusion sacrifices localized terrestrial flexibility to construct a lightweight airframe capable of withstanding the violent torsion of flight. Moving from macroscopic physics to microscopic cellular biology exposes the metabolic demands of avian reproduction. Reproductively active females develop a specialized transient woven tissue inside their marrow cavities, known as medullary bone. At the cellular level, hyperactive osteoclasts rapidly resorb this spongy medullary mire, mobilizing stored calcium to direct toward the uterus for eggshell formation. In high-producing commercial laying hens, continuous daily egg production can outpace dietary calcium intake, causing systemic depletion. Starved for calcium, the hyperactive osteoclasts begin cannibalizing the bird's structural cortical bone. This leads to a severe osteoporotic condition known as cage layer fatigue. This image highlights the macroscopic consequence of that microscopic osteoporosis. The yellow arrows indicate deformed, undulating fractures along the keel bone, an area that fails structurally when cortical bone is stripped away. A different metabolic vulnerability emerges from the rapid growth demands placed on modern commercial poultry, leading to failures in endochondral ossification. When the physical growth of the bird outpaces the vascularization of the bone's growth plate, the transition of cartilage into mineralized bone halts. This failure is called tibial dyschondroplasia. As we see in the affected bone on the right, an unvascularized plug of cartilage accumulates in the growth plate, preventing proper ossification and causing severe lameness. Pushing the avian skeleton to its metabolic and developmental limits triggers structural failure and physical collapse. Away from these extremes of exertion, the avian skeleton also dictates how the animal conserves energy while at rest. The lower legs and feet contain an automatic perching mechanism that operates with high mechanical efficiency. The deep digital flexor tendons run down the back of the tarsometatarsus and route directly underneath the toes. The simple act of crouching changes the geometry of the joint. Bending the ankle pulls the tendons taut over the bone, snapping the toes downward. This creates a mechanical lock. The bird maintains a vice-like grip on a branch while sleeping, requiring no muscle contraction and burning no metabolic energy. From terrestrial rest to the extreme kinematics of flight, the avian skeleton functions as a highly specialized system. Its architecture reflects a precarious balance between the laws of aerodynamic physics and metabolic capacity.